All right, back. This is page 2, notes 20, Calc AB. We're talking about area of a region bounded by curves. And the very basic idea is in this box, so area between curves. F and G are continuous on a closed interval from A to B. F of x is always the top curve, so f of x is greater than or equal to g of x for all x in the interval. The area bounded above by this, so that means it's the ceiling, right? It's up above and below by g of x. That means it's on the floor. I don't know why, but I have students every year who have trouble with bounded above versus bounded below. It's kind of weird because like one's just the roof and one is the floor, but like whatever. On the left by A and on the right by B, whatever. This is just too many words. This is what I always think of. So it's the integral of top take away bottom from left to right. That's it. That's all you got to do. Integral of top take away bottom from left to right. And that's going to give you your answer, right? So these are the most basic type. There's like a lot of little like things, but this is the idea. You're always, if you're integrating with respect to x, which we'll talk about, but it's going to be top take away bottom from left to right. Not a big deal. So what you want to do, if necessary, you're going to have to find some intersection points. Often you're just given bounds, but if you're not given bounds, it must mean that the curves intersect somehow, and we'll have to work out where. Identify which curve is on top and which is on the bottom, obviously. If you can't work that out, then what we're going to do is just plug in a value and see, right? So if you're integrating from 1 to 12 and you're not sure which is on the top, plug in 5 and see which one gives you a bigger value. The one that gives you a bigger value must be on top, so you do top take away bottom, top function minus bottom function. Then evaluate the integral. That's it. So let's see if we can do it. So sketching the region is a big deal. Often I'm skeptical of the use of like sketching a really good thing, but sketching anything is better than sketching nothing. So here we go. Like this, x squared, kind of like that. Square root of x, kind of like that. They actually intersect at 1. So if we have x squared equals radical x, do I want to solve this? I do not want, well, I mean, I'd square it and get x to the 4th equals x, and then x to the 4th minus x equals 0. And I factor in x, and I get x cubed minus 1. That's a difference of cubes. Get x equals 0, x equals 1. Yeah, those are the only intersection points. So you know they intersected 0 and 1, but it turns out that 1/4 for some reason is one of the things we're going to use, and then 1 is the other one. So the region that we're dealing with is this region. So we're going to set it up, right? We need top. So the top curve is going to be y equals the square root of x. The bottom curve is going to be y equals x squared. So draw your pictures. Drawing your pictures is kind of the key thing. Go from 1/4 to 1. The top curve, which I'm going to write as x to the 1/2, minus the bottom curve, which is x squared. Give it a dx. Fundamental theorem. That's it. So 2/3 x to the 3/2 minus 1/3 x cubed from 1/4. That 1/4 is super unhappy. 2/3 minus 1/3. That's interesting. 2/3 minus 1/3, and then minus 2/3. So 1/4. The square root of 1/4 is 1/2. Cubed is 1/8. 1/8 minus, oh my god, why would anyone do this? 1/3. Then 1/4 to the 3rd is 1/64. All right, and if the point of this video was to watch me do arithmetic, I would do this, but it's not the point. So what I'm going to do is I'm going to switch to the calculator, and I will do both. I'll do the definite integral, and then I'll like check mine and see how it went. So let's see. You can define the functions, or like oftentimes it's just faster to go for it, right? So I want to go 1/4 to 1 square root of x minus x squared dx. There you go, 49/192. I was headed toward 2/3 minus 1/3, but obviously 1/3, and then 2/3 times 1/8 minus 1/3 times, this is where I find out that I was wrong and it's really annoying, 49/192. Woo! All right, so like be able to do that, but like that's not why we're here. So I'm just gonna let the calculator do some calculations for us when the time comes. All right, so we got it. very nice. Set it up, evaluate it. Really, one of the keys is going to be drawing the picture. It doesn't need to be perfect, but it's got to be there. All right, so here, our region is weird. It's this. This is the y equals 0 is the x-axis, x equals 0 is the y-axis, x equals 2 is like a random vertical line. This, I don't know. I'm going to factor it. So that's going to be x squared minus 4, so x plus 2, x minus 2. Okay. It can be really helpful to have some idea of what the actual thing looks like. All right, so at -2, 2, and 0, what is the scale that I'm using? Hold on. Let's concentrate on graphing this weird function first, and then we'll worry about the other stuff. So it has a 0 here, it has a 0 at -2, and it has a 0 at +2. And then it's a positive cubic, so positive cubics go like this. Okay, so the region that we want is bounded by the x-axis, the y-axis, and x equals 2. So this, do we really need the y-axis? I mean, I guess we do to like tell it to stop. Here's the region. Now, what is the top curve? The top curve in this region is y equals 0. The bottom curve is y equals x cubed minus 4x. So let's set this up correctly. So we want to do the integral from 0 to 2, because that's where you start on the x and that's where you stop on the x. And then the top curve is 0 minus the bottom curve is x cubed minus 4x. And dx. Okay, we're set. Let's do this. So 0 to 2 of negative x cubed plus 4x dx, negative 1/4 x to the 4th plus 2x squared. Fundamental theorem, man. I'll be using it all the time. All right, negative 1/4, 2 to the 4th is 16. Negative 4 plus 8. That's when you plug in that. And then minus, when you plug in 0, you get 0. I believe we're going to get 4. Let's check it out. Let's see. So back to the calculator. I'm going to do two different things. I'm going to do the integral of 0 minus quantity x cubed minus 4x. You should just use the template. So I get 4. All right, good. Let's look at a graph. So I am extremely skeptical of the graph's ability to do these, but x cubed minus 4x. And then also I need to graph 0 because I'm going to ask the calculator to find the area between curves. And so to do that, I need the two curves. So I'm going to do menu, option 6. And if you look at option 8 here, it's bounded area. You might need to upgrade your operating system if that's not an option. So the lower bound is 0. The upper bound is 2. And you can see, there it is, it's 4. It even shades it for you. I don't know why I'm skeptical of it. I'm just skeptical that it's like going to work always. So, whatever. Your mileage may vary on that. Don't let my skepticism impact you, but I would always do it on the calculator page also, just to like make sure. I mean, what's nice is that it shades it for you. And that's a pretty good deal. I'm gonna do one more and then skip to the next video. I'll do the rest of them. All right, here we go. Secant squared. Do I even know what that looks like? Not really, but do I need to? Kind of. So let's see how we can work this out. So cosine, secant's the reciprocal of cosine. Cosine looks like, hold on, I'm going to switch this up a second. Cosine looks like kind of this, right? Man, the dashed lines really highlight how poorly I was doing that. So secant's the reciprocal of that, and secant squared is just going to be like more extreme. It's going to be like, All right, but the key thing here is that cosine has problems. Well, it doesn't have problems. Secant has problems at pi over 2 and negative pi over 2. But negative pi over 4 and pi over 4 are in the interval, so that's not an issue. And then I'm going to also add y equals 2 because this was at 1, This is at 2. So the region that we're dealing with is here. So we got to do top, take away, bottom. So it's going to be the integral, negative pi over 4 to pi over 4. This is actually an even function, so we could do 2 times the integral from 0 to pi over 4, which is probably a better idea. 2 minus secant squared of x dx. But this is all straightforward. So I'm going to do 2 times the integral from 0 to pi over 4, because I think that's going to be easier. 2 minus secant squared of x dx. All right, so 2, we get 2x minus the derivative of tangent is secant squared, so we get tan of x, which is pretty much how I do that. I look at it and I think, what is that the derivative of? Not how do I find the antiderivative of that? Which, like, I mean, they're the same sort of thing, but, like, you know, a tiny little bit different. All right, 2, plug in pi over 4, you get 2 times pi over 4 is pi over 2. The tangent of pi over 4 is 1. Plug in 0, you get 0, and the tangent is 0, 0. So we get pi minus 2, potentially. Let's see what the calculator says. So pi minus 2. I think if we do this on the graph, it's not, I think it's not going to give us pi minus 2. I think it'll give us like 3.14 minus 2 is like 1.14. That's what I would expect. Here, I'm going to do the integral 2 minus secant of x squared, comma x, from, I'm just going to negative pi over 4 to pi over 4, right? Like, why take those human skipping things? Pi minus 2, outstanding. We did slightly different, right? We did 2 times the integral from 0, because that's what you should really try to do with an even function. If the bounds are symmetric, it's just like a little easier. Let's graph secant of x squared, and then 2. Okay, now let's ask it. Menu 6, option 8, lower bound, negative pi over 4. Upper bound, pi over 4. Okay, I don't know what's happening here. Lower bound, negative pi over 4. And then, okay, so this is, remember when I said be skeptical? Like, I don't know what's happening. Lower bound, negative pi over 4. Upper bound, pi, why? Why would you not? Upper bound, pi 3.14, minus 3.14 plus pi over 4. So I'm like sneaking my way in here. I don't know why it won't let me do it, but like this is a workaround. Just do like 0 minus 0 and then plus, or do 0 plus. There we go, 1.14. But that was annoying, right? So like we had to find a way around it, which I advocate, right? Like every time, never let the calculator tell you it won't do something when you know it will. But I don't know why I had to do that. So I'm going to go back to the notes. You can take a look at this one more time, and then I'm going to come back in the next video and finish this page. And we're off and running. I mean, if you're able to identify the top curve, the bottom curve, and do the fundamental theorem, you challenge accepted, right? All right, there it is. So I'll be back in the next video to finish this page, and I will see you there.